All right, welcome back. We're going to study section 2 from chapter 1, sampling from a population. And there are three basic things that we want to cover in this section: samples, bias, and simple random sampling. And let's begin with samples. And in order to understand samples, we have to understand the context from which samples are drawn, and that's the idea of a population. And a population is something that we have to infer oftentimes from the study in question. So a population includes all individuals or objects of interest. And an easy way to kind of get into thinking about this is to just look at some examples and understand from the question that's being asked, can we draw out of it the intended population or set of objects of interest? So for instance, we could be studying the question, do university students support the legalization of marijuana? Suppose we saw the report of such a study. It would be wrong to think about this study as saying something meaningful about all the people between, let's say, ages of 18 and 22. The intended population for this study is university students and whether or not they support the legalization of marijuana. So the population here is clearly university students, and the question of study is whether or not they support the legalization of marijuana. Okay, do retired people favor the Republican candidate? Again, this is not a question of whether people in general favor the Republican candidate. The question is, do retired people favor the Republican candidate? So the population of interest here is the retired people. Do Furman students want to change the dining hall management company? Again, the population of interest here are simply the Furman students and not all university students. What fraction of the cars on a production line will pass a 20-point inspection? Now, this example is a little different than the other ones because there's a hypothetical quality to this example. So when we're thinking about the cars on the production line, there's a sense in which it's not simply the cars that are currently on the production line and whether or not they will pass the 20-point inspection. We're also thinking of the cars in the past, and we're also thinking of the cars that might be rolling down the production line in the future. So there's a hypothetical quality to this question that in some sense consists of cars in the past, the present, and the future that have or might be soon rolling down this production line. So that's a little bit different in that we can't simply point to existing objects, but we have to think of it more hypothetically. But nonetheless, that forms a population for us. Okay, now, there's a couple of different ways that we can investigate a population with regards to a question, and a lot of this has to do with how big the population is. So one way of studying a population is to conduct what's called a census. So in a census is a study of every unit, everyone, or everything within a population. So when we think of studying a question within a census, we're imagining inquiring of every single subject or object and collecting all of the relevant information for every single subject. All right. By contrast, a sample is a subset of units in a population selected to represent all the units in a population of interest. Okay, so it's a way of gaining information about the entire population by querying a subset of the population. So that's what we mean by a sample. All right, so a nice way to think about the difference between these two is we should think of a census as being conducted on the entire population, whereas when we're working with a sample, we're selecting a subset of that population and querying only the individuals in the sample. Now, you can kind of see the difference between these two, right? That the sample, we hope, is big enough and is representative enough of the entire population so that anything we say about the sample can be inferred about the population as a whole. More on that idea in a little bit. Okay, so why use a sample? Statistical inference is the process of using data from a sample to gain information about the entire population. So when we're thinking about using a sample, we're thinking about making some conclusion about that sample and then inferring it back to the population as a whole. So it's as if we have a picture like this. We want to know something about the entire population. We extract a subset of the population. We set it aside. We query our sample. We collect information about the sample, and then we infer that information back to the population as a whole. And that process is called statistical inference. It's the inferring of something from the sample back to the population as a whole. Now, there's two main problems that you might run into. Your sample might be too small, and your sample might not be representative of the entire population. So any conclusions you're making about the sample, it may be difficult to infer them back to the population as a whole. So those are always two main concerns in doing any kind of statistical study. Is my sample big enough? And is it representative enough? Okay, so two main roadblocks to using statistical inference. Now, before we leave this first topic here, let's kind of look at censuses and samples, put them side by side, think about the pros and the cons of each of them. All right, so when we think about a census, the pro of working with a census is that you have complete information about the population. You know everything. There's no need to do statistical inference when you have complete information from a census. What is the main con of working with a census? Well, it's hard to collect data about every individual in the population, especially when the population is very, very large. Okay, now, the United States, by law, has to conduct a census every 10 years. And so that's mandated by law. So every 10 years, we have to go through the rather arduous process of collecting data from the entire population. But that is a lot of money and a lot of time spent to collect that data. So that is the main con of working with a census. Now, working with a sample, the main pro is that once you have the sample, it's much easier to query that set of individuals or objects and get the information that you want. Okay, now I put the word easy here because it's easy to collect the information, but there may be some good hard work in informing that sample, making sure that it's representative and making sure that it's large enough. So when I say easy here, I'm simply saying it's easy to query the sample to get the information you want. There still might be a good bit of hard work in going to make sure that that sample is representative and large. Okay, now what's the main con of working with a sample? It's the inference. It's the working backwards from the sample to the population as a whole. Okay, so the main con in working with a sample is there's always going to be that bridge from the sample back to the main population, that active inference, and you may lose some information or some credibility as you work from the sample back to the population. So that's the main drawback. Now, let me just, before we leave this little subsection here, let me just pose a question to you. Would we rather work with a census or a sample in the following scenario? So, is vaccine X safe for use in humans against a coronavirus? Now, I will argue that it would be much better, right, to collect a group of volunteers that in some sense represent the entire population, at least within ethical bounds, and test this vaccine on that sample. And if it seems to work on the sample, we would make a valid inference and say it looks like it would work safely within the population as a whole. So sometimes there are just good ethical grounds that guide our process here, and we say, well, it doesn't make sense to give the vaccine X to everyone, but it makes more sense to work with a set of dedicated volunteers that in some sense represent the entire population. Okay, so that's the end of this first subsection on samples. Let's move on to the next topic, which is bias. All right, so our next topic, and a very important topic, is the topic of bias. This is going to be a problem that's going to haunt you if you're doing statistical information and you've imparted bias into your work. All of your inference will be for naught if you don't try to control bias. Now, what are we talking about here when we're talking about bias? It's always the question of, does the sample resemble the population? I'm extracting a subset from the population. I'm studying the sample. I'm going to try to do the act of statistical inference to infer results from the sample back to the population. Now, Does the sample resemble the population? There's a couple of ways that this can go wrong, okay? And you should understand that and design your study accordingly, right? So it could be that you've just got very bad methods for selecting the subset from the population, so you end up with a non-representative sample. Therefore, results about this sample may not be reflected within the population as a whole. So you have to make sure that you've got good methods for selecting a representative sample from the population. Another thing that can happen, and this happens often when you are conducting a survey and you rely on the people that you've selected to send the survey to, you're relying on them to respond to your survey. So you can impart what's called response bias, because people may or may not feel inclined to respond to your survey. So there's a possibility that all you're getting from your sample is a subset of those that you've already sent the mailing to, and there's a bias that might be imparted in those who respond to your survey. So we have to be careful about that. Now, all I want to do in this little subsection on bias here is give some names to some typical types of bias and study some kind of classic examples of these forms of bias, just so that you're aware that they're out there. And if you're doing a statistical study, you won't fall into the same kinds of traps. Okay, so let's take a look at what's called sampling bias. So sampling bias occurs when the method of selecting a sample causes the sample to differ from the population in some relevant way. If sampling bias exists, then we cannot trust generalizations from the sample to the population. Okay? So there could be a problem just in the selection of the sample. So we'll call this selection bias. Selection bias is the bias introduced by selection of individuals, groups, or data for analysis in such a way that proper randomization is not achieved, thereby ensuring that the sample obtained is not representative of the population intended to be analyzed. Now, a classic example of this, and one that you may have heard about, is the famous 1936 Literary Digest poll. Now, the Literary Digest was one of the most popular magazines of its time and had an outstanding record of predicting winners of presidential elections. So the Literary Digest up till 1936 had a stellar record for predicting the winners of the presidential elections. Now, in 1936, the presidential election pitted Alfred Landon, or Alf Landon as he was called, the Republican governor of Kansas, against the incumbent president Franklin Delano Roosevelt. And for the 1936 election, the Literary Digest predicted that Landon would get 57% of the vote against Roosevelt's 43%. The actual results of the election were 62% for Roosevelt and 38% for Landon. They got it almost backwards. And the question is, what went wrong in 1936? Why all of a sudden were they having problems? Well, it wasn't the sample size. The sample size was enormous. This was not the issue. They sent out surveys to 10 million people. So it was a very, very large and very worthy effort on the part of the Literary Digest. Now, what did they use, though? They used telephone directories, lists of magazine subscribers, rosters of clubs and associations, and other such sources. A mailing list of nearly 10 million names was created, and every name on this list was mailed a mock ballot and asked to return the marked ballot to the magazine. The sample was biased in a couple of ways. First, the mailing list was likely biased towards middle and upper class people, right? They're going for people that had telephones, magazine subscriptions, and were parts of clubs and associations. So it was probably leaving out a very large subset of the population that had none of those affiliations. And the second is, the people that do not respond to the poll might be different than the people that respond to the poll. All right, so there may have been some bias in forming this sample in a couple of different directions, but certainly already the sample was going to be selecting from a set of the population that was probably slightly more affluent and therefore slightly non-representative of the population as a whole. Okay, so that's a very famous example of imparting bias through actually the selection procedure. Another kind of bias is what's called survivorship bias. And survivorship bias or survival bias is the logical error of concentrating on the people or things that have made it past some selection process and overlooking those that did not, typically because of their lack of visibility. All right, so an example of this is trying to understand, we'll call it caveman bias, and this is trying to understand our very, very ancient ancestors by looking only at the durable goods that have survived these many, many thousands of years. All right, so all we have left are some of their very, very durable goods, cave paintings and stone tools, and it would be hard to say anything meaningful about how they actually lived based on just the artifacts that have survived. Another famous example, and one that we should always remember, is the example of Abraham Wald and the so-called story of the missing bullet holes. And this is an example that comes from World War II. So during World War II, Abraham Wald was working for the Statistical Research Group, the SRG, which was a classified government program. And his story is described really nicely by Jordan Ellenberg in his book, How Not to Be Wrong. And he describes one of the problems that was given to this statistical research group. You want to protect your planes from being shot down. So where should you put the armor, right? And this is what Ellenberg writes. He says, so here's the question. You don't want your planes to get shot down by enemy fighters, so you armor them. But armor makes the plane heavier, and heavier planes are less maneuverable and use more fuel. Armoring the planes too much is a problem. Armoring the planes too little is also a problem. Somewhere in between, there's an optimum. The reason you have a team of mathematicians stocked away in an apartment in New York City is to figure out where the optimum is. So where do you put the armor? You don't want to put on too much armor. You don't want to put on too little armor. Where should you put the armor? Well, here's the data that the statistical research group had to work with, right? They looked at the planes that came back, and they realized that the bullet holes per square inch were distributed around the plane as follows, right? In the engine, 1.11 bullet holes per square foot. In the fuselage, 1.73. In the fuel system, 1.55. And in the rest of the plane, 1.8. So based on this information, where do you put the armor on the plane, right? So the group studied the data from the returning planes, and we have to be careful not to think too quickly here. What can we learn from this data? See, Wald understood that the returning planes do not form a random sample of all the planes that have been hit by bullets, right? This is a case of survivor bias. You're only studying the planes that got back. In fact, the planes that you would most like to see, the ones that actually got shot down, are not in the sample at all. So what do? The ones that we would most like to examine are the ones that got shot down, but they're not here. Wald argued that you should armor the planes to protect the engines. That's the one that actually has the least bullet holes per square foot. Wald argued that you should armor the planes to protect the engines. And as Ellenberg writes, the reason planes were coming back with fewer hits to the engine is that the planes that got hit in the engines weren't coming back at all. And this is a classic case of survivor bias. We can only learn so much from the planes that come back, and we really, really want to know something about the planes that didn't come back. So we have to be careful in thinking too quickly in a situation like this. Another example is participation or non-response bias. This is another way of imparting bias, right? So participation bias and non-response bias are phenomena in which the results of elections, studies, polls, etc. become non-representative because the participants disproportionately possess certain traits which affect the outcome. So, for example, do test prep courses boost scores? Now, we would have to be careful about a study like this because it could be that the kinds of people that take test prep courses are not representative of the entire population, right? So Maybe only very highly motivated children or highly motivated parents or families with some wealth can afford to do a test prep course, and therefore we might be suspicious of any result that talks about how great these test prep courses are to boost scores, because the people that are taking these test prep courses may not represent the population as a whole. This is also something that can happen if we're doing surveys by mail and we're relying on the people that receive the surveys to respond to the surveys. So oftentimes the people that respond to the surveys are going to skew the results in a certain direction, and we have to be attentive to the fact that many people will not respond to our surveys, and that could be imparting some bias into our work. Okay, so be careful about that. Now, one last thing, and the textbook doesn't really talk about this too much, is you also have to be very careful in how you word your survey questions, right? You have to be careful in how the questions are phrased and formatted. And there are professionals that do this kind of work for a living. So if you're going to be doing something and you're concerned about the phrasing of your questions and how you're conducting the survey, you should consult one of these professionals, or at least consult a good book on this to make sure that you don't impart bias just in the way you're conducting your survey. So here's an example, right? You could have a question like, how happy or unhappy are you with the rate of current school board funding and the Common Core curriculum? Asking a person to respond to this kind of question, it's going to be difficult to know what to do with that answer, because for one thing, you're forcing them to think about two different things and kind of form a single response. And you're also kind of forcing them to look at a hot button issue, a current hot button issue like the Common Core curriculum, and then taking their feelings about the Common Core curriculum and attaching that to questions about school board funding. So maybe someone who's very unhappy that the school board is working at implementing the Common Core curriculum, they might want to defund that school board. And so they'll answer negatively about the rate of school board funding. All right, just a concern that you should be aware of. Another thing that might happen is you might put some kind of weasel words in your question that will kind of skew people to thinking one way or the other, right? So should concerned dog owners have their pets vaccinated, right? So now you're asking yourself as you're answering this question, well, am I a concerned or an unconcerned owner of a pet? So again, we have to be careful about is the very nature of the way we're asking the question imparting some bias in the responses. Okay, again, consult a professional if you're very concerned about the format of your questions. All right, our next topic is going to be simple random sampling. Let's move on to that. All right, so our next and last topic within this section is simple random sampling. And simple random sampling is the chief way that we're going to try to overcome bias. All right. When choosing a simple random sample of n units, all groups of size n in the population have the same chance of becoming the sample. As a result, in a simple random sample, each unit of the population has an equal chance of being selected regardless of the other units chosen for the sample. So when we're thinking of simple random sampling, we're thinking of our population as let's say, slips of paper inside a gigantic box. And we're like pulling raffle tickets out of the box. We're saying select 10 people from the population. We're just reaching in and randomly selecting the 10 slips of paper or the 10 index cards out of the box. And so that's our image of simple random sampling. Here's a concrete example. And again, I have to use a very small example because the combinatorial explosion that occurs once our population grows to a certain size and once our sample grows to a certain size. So think of this simple example here where I have a population that consists of 4 individuals labeled A, B, C, and D. And I want to look at drawing a simple random sample of size 2 from this population. What I have to envision is all the different ways that I could select these individuals out 2 at a time. And there are 6 different ways to do this. For instance, I can have A and B paired, A and C, A and D, B and C, B and D, and C and D. So when I'm thinking of forming a simple random sample of size 2, I'm imagining that any one of these 6 is equally likely to be picked. So in a simple random sample of size 2 from the set A, B, C, and D, any of these 6 pairings is equally likely to happen. Okay, so that's the idea of a simple random sample. Now, here's the question, right? Practically speaking, how could I randomly select 4 students from our class? How could I do that, right? So one way is to imagine putting all of your names on slips of paper, putting them into a box, shuffling the papers very, very carefully, and then pulling them out blindly until I've produced a sample of size 4. So I could think of slips of paper in a hat or slips of paper in a box. Another way is to use some technology. There's a website called random.org that will help you randomize things. So you can just go to random.org, and you can work on it with what's called a list randomizer. So I can take the names of students in a class, pipe them into random.org, and it will take the list and put it into a random order. So let's take a look at an example of this. I'm going to use a fake class here. I've got the names of 40 different students, 20 females and 20 males. So I'm going to take their names. I'm going to put them into random.org. There they are, from Emma down to Henry. And I'm going to ask it to randomize this list. And it's going to use some procedures that it has built in. And it's going to take that list of 40 students and it's going to put them into an ordering from the first student to the 40th student randomly. Okay, now if I want to select 4 students from this class, all I have to do is to take the top 4 people in this list. So that'll be Mason, James, Grace, and Ella. Another thing I might want to do is split the class into groups of size 10. And so I can take 1 through 10, 11 through 20, etc., until I've got the class partitioned into 4 groups of size 10. You can let your imagination run wild here, but random.org is a very, very efficient way to take lists and randomize them. Again, the image, though, should be slips of paper in a box, all right, and pulling slips of paper out at random. Random.org is just allowing us to do that very, very efficiently. Okay, so that brings an end to section 1.2. I hope you learned some things about the various topics that we were studying in this section, right? Samples, bias, and simple random sampling. I'll meet you again when we discuss section 1.3 of the textbook. All right, so I'll see you then. Take care. Bye-bye.